video on analog electronic circuits laboratory. So in this video we will see how do we do the report for DC power supply experiment. These are the prerequisites. Because by this time you know what is diode and its application, line and load regulation. Okay, with these prerequisites, let us start the. Okay, this is at the template of the DC power supply. Of course, this particular report has uh, a design specification for DC power supply design. So we want a plus 5 volt DC voltage using half wave rectifier, and actually this is minus 5 volts, minus 5 volt using full wave rectifier using two diodes, and again plus 12 volt using bridge rectifier. So these are the objectives. We want to realize plus 5 volt DC. This is actually minus 5 volt DC, and this is plus 12 volt DC using different rectified circuits. And of course, we're going to use corresponding regulators to get the plus 5 volt, minus 5 volts, and plus 12 volt using different rectified circuit. First of all, okay, we are writing the circuit diagram and its corresponding waveforms, which has been already discussed in the previous videos. You can see this is a half wave rectifier. Using half wave rectifier, how do we realize plus 5 volt? So we know that we are having a 5 volt regulator which is 7805, and there's a half wave rectifier. There's a capacitor filter C, and this is the 230 volt 50 hertz AC signal, and I have written the waveforms here. So V1 dash is a waveform at the input of your rectifier, which is this dotted one, and suppose if you simply connect a resistor, you can see this V2 you will get. So V2 is nothing but the waveform of the half wave rectified signal. The moment you put the capacitor, so you're going to get this ripple voltage. That's what is V2 dash. So at this point we're going to get V2 as well as V2 dash. So V2 is when you have just the resistor, V2 dash resistor and the capacitor, and this final one, that is V3, that is a constant 5 volt at this point, is the regulated output voltage. So these are the waveforms you are supposed to get in the report. So this is the circuit diagram and the waveforms. So coming down here, so this is if using full wave rectifier, how do we realize minus 5 volt? So we know that minus 5 volt requires 7905. So, and of course you can see this is ground and this is input. Carefully observe, this is a electrolytic capacitor will have polarity. So plus is connected to higher potential, minus is connected to a lower potential here. The same thing is applicable here. Since this is negative voltage, since we connected the diodes in the opposite direction compared to the positive voltage regulator, so we'll be getting a negative voltage here, but here it is 0. Since we know that 0 is more than negative voltage, so that's why this positive is going to ground. And you can see this is the waveform. V1 dash is again at the input, V2 dash again without capacitor, with capacitor, and the regulated voltage which is minus 5 volt. This is what is the circuit diagram and the corresponding waveform. Since the diodes are connected in this fashion, we're going to get the negative halves only. This positive half will also be flipped down to the negative half. So that's what is the full wave rectifier. Then comes the bridge rectifier using to get 12 volt using bridge rectifier. So we are using 7812, which will give you 12 volt regulation provided you have sufficient input voltage at the input of regulator. So that is realized using a bridge circuit, and you can see this is the waveform at this point, which is V1 dash, and again this is V2 and V2 dash. V2 is with resistor, V2 dash is with resistor and capacitor, that is the filter one. Of course, this has been already discussed in detail in the previous videos. Fine. So these are the circuit diagram and the waveforms. So that's what the first portion of your report should include, that is circuit diagram and waveform. So once you're thorough with the circuit diagram and what is expected to get at different nodes, then comes the assumptions and design. So now these are some assumptions made. So we are assuming that let all regulators have a 2 kilo ohm as the input impedance. So we are assuming a ripple voltage of around 500 millivolt, and these are some assumptions which have been made from the data sheet. So meaning to get constant 5 volt you require minimum 7 volt and maximum of 20 volt. uh, of course, to have this 7 volt minimum, so we are having the input voltage of minimum 10 volt, which is uh, more than 7 but less than 20. And of course, you can see this is what is, this should be more than 7, and V2 dash max should be less than 20. So we are ensuring that it is coming within the band of this. So this data is coming from the data sheet. Fine. We know that V2 dash max. Now it comes the design part. So V2 dash, what you want is V2 dash max is V2 dash minimum plus the ripple voltage, and from that you can find the value of C, assuming a ripple voltage of 0.5 volts, and V2 dash, we know V2 dash max is known to be 10.5. You know the frequency, you know the value of R as 2 kilo ohm. So when you find the value of C, it comes out to be 210 microfarad. So similarly, we are doing the design for the capacitor value for different filters and their corresponding V2 max, V2 dash max. So this is what, okay, for a half wave rectifier you require 210 microfarad. For a full wave rectifier using a bridge you require 105 microfarad capacitance, and for the bridge you require because now since you want to have a 12 volt regulation, you can see since you want to have a 12 volt regulation using the bridge, so since the input voltage itself is more, which is 18.5, it actually requires a larger capacitor voltage to get a smaller ripple voltage. So this is what is we are having, and then we are trying to find out what should be the rating of the secondary of the transformer. So that's what we are writing here. V2 dash max is nothing but, so what I'll do is, let me just open this in another, let me just open it with Firefox also, so that I can simultaneously show you both the, okay. So what I'm trying to do is, so let me put this here, and let me, so when I'm explaining this here, so I'm referring to these circuit diagram, these waveforms. So now let me further reduce this. Okay, now if you see here, this V1 dash max is nothing but this peak V1 dash max. So that is V1 dash max is given as V2 dash max plus 0.7. That is the maximum voltage that you have is this. What is this? Is that voltage. So what you want to know is what is V1 dash max, because you know this. So you need to add a diode drop of 0.7 to get this voltage. So since you know this V2 dash max, since you know V2 dash max, you add 0.7 volts, that is this diode drop, you will get what is the peak voltage required at the secondary of the transformer. Once you know the peak voltage, you can find its RMS. This happens to be the rating of the transformer. So 7.91 volt is the secondary RMS voltage required to get a corresponding voltage, so that you can get 5 volts here. So similarly, we are doing it for full wave rectifier. So for full wave rectifier, it's the same, because whatever voltage maximum you have, the voltage that will be actually plus of that. Of course, even of course we are talking about negative voltage here. So negative, because this is a AC signal, whatever you do it for plus 5 will be valid for minus 5 also, because this is a AC signal. So whatever positive half you have, the same will be negative half. So that's why even though we are designing it for minus 5 volt, since I'm taking the modulus of that negative voltage, you can see now it comes out to be 11.2 volt peak, which again requires a RMS of 7.91 volt. So if you are using a 909 transformer, So that will be more than 7.91. You can comfortably do it. Then coming to this, you can see for this bridge, the voltage, this V2 dash max and V1 dash max, in between that you actually have two diodes coming in series. So that's why V1 dash max is V2 dash max plus 1.4. This 1.4 comes from 2 times V gap. So you want to have a RMS voltage of 14.07. You can use 015 or 909. So in that 0909 you use the two extreme, that is it will become 18 volt, which will be certainly more than 14 volts. Okay, now this is how you can able to relate these transformer ratings to the circuit diagram. Then comes, so now we are having the values of capacitor as well as the rating of the transformer has been found out. Then comes what is the actual component that we'll be using. Okay, this is what is done here. Now this is what you're choosing for. So you actually want, if I just again go back and say what is this, so what I'll do here is, so this is my uh, so here let me just go to next page, and these are the values that what you got, and the components that you are available in the lab are typically what will be available is something like this. So you may not have exactly 200 and just a minute, you can see now for half-wave rectifier, give me a minute. So this is for half-wave rectifier. For half-wave rectifier, what actually we found is 210. So 210 microfarad is not exactly available. I think we have, this is not even 240, so it's actually 220. So you have a 220 microfarad, which is a standard one, and here you can see you have 105 as a design one, but what actually available is 100. You can use 100, and again you have 185 standard is not there, so you go for 220. So this is actually 220. And transformer rating what you have is 7.91 RMS. You don't have that, you use 09. Again, since it is center tap, use 909. Since you want to have 14.07, you don't have that, you can use 15.0 or 909 and two extremes. And ripple voltage you can take it as if you can find the ripple voltages here. So upon ripple voltage, you can, of course, if you take the ripple voltage, so we are taking the ripple voltage as around 0.5, 0.6 and 0.4. So these are the ripple voltages what we have calculated upon using these values of C and the corresponding value of R, and using this value of RMS voltages. So this is what is the values we're going to get. So this is what you're getting. So 0.5, 0.6, 0.41. Because when we actually started, we assumed let all of them have a 0.5 ripple voltage. This is what our assumption. You can see this was our assumption. 0.5 volt millivolt ripple voltage. Sorry, 0.5 volt ripple voltage for all the circuit. But it is ending out to be 0.5 for half wave, and maybe 0.6 for full wave, and 0.4 for bridge. That's fine. So they're around 0.5 volts. So that's how you got this V ripple, and then V naught is 5 minus 5, 12 volts. So this is what your next comes the conduction. So you're supposed to conduct the experiment and start taking the screenshot correspondingly. So now if you can see the first waveform what you'll be taking for the half-wave rectifier is the input voltage. So that's what is this. See now the first and foremost waveform is the input waveform. Let me slightly minimize this. So in this you make sure that you are measuring the maximum voltage, and you are measuring let me just show you what is that can be measured. Let me hide this. Okay, what is that is measured is, where is that? Okay, let me slightly minimize this further. See now, you are measuring, so you're measuring what is maximum voltage and the average voltage and the frequency. You can see frequency is 50 hertz. Okay, so it is, frequency is 50 hertz, maximum is 15 point something. So can you see how much is that? It is around 15.6 and average voltage almost zero. Then comes input and the rectified. So now this is your rectified signal. See here again, it is maximum average of C1 and C1 frequency, C2 maximum and the average voltage of C2. So this is your DC voltage of the output voltage. This is a half rectified signal. Then comes the input sine with the filter. So this is your input sine wave with the filtered waveform. Here you'll be measuring the peak to peak of C2, which will give you the ripple voltage. Fine. And then comes the filtered and the regulated. Can you see this is a filtered waveform and this is a regulated waveform. So what we are trying to see here is, so if you see this, in the first case we are just measuring the input voltage, then input and the rectified one. When you're finding the rectified, you're going to remove this capacitor, then the input and the filtered one, and the filtered and the output, filtered and the output. So always we tend to measure the input using channel 1 and output using channel 2. For regulated one, this becomes the input, that is V2 dash, and this becomes the output, that is the regulated voltage. So that's why you can see here what we have is, this is the filtered waveform, this is the output regulated. You can see output regulated is almost 4.98 volt, the input is around 13 volt, and it has got a peak to peak of 367, the input peak to peak, whereas the output peak to peak is almost fairly constant at 55 millivolts peak to peak. Almost there is no much variation, and it has got a constant voltage of how much, where is that, 4.98. So this is the regulated output voltage of this circuit. Which circuit? This circuit, this one here. Then comes the line regulation. To do the line regulation, what we have to do is, so now this is the line regulation. So what we are doing here is, if you can see here, this is my circuit diagram. So let me just write it over here and try to tell you what happens in your line regulation. So this is the transformer where you have a 230 volt 50 hertz AC signal. You have the secondary. This is now this is 7805 without the capacitor. So what are the waveform we'll be having? The waveform that you will be having is something like this. So if I say this is V2, V2 is actually something like this. This is V2. That becomes the input to this regulator. We know that this regulator requires 7 volts to get the constant phi. So now till the input is 7 volts, output will not be 5. So for more than 7 volts, output will be 5. So what happens is, your output goes something like this. See now, here it comes. So this voltage is 5 volt. The corresponding input voltage is 7 volt. So and then it goes like this. See, when the input voltage is more than 7, output will become constant phi. So how do you get this waveform? For that I have to remove the capacitor. So I need to apply voltage from 0 to some larger voltage, 0 to maybe around 15 volt or 16 volt or 20 volts. So when you are varying from 0 to 16, this is V in, this is V naught. Till 7 volt, output voltage will be not equal to 5. After that it will be 5 volt. So this is what is line regulation. So that's what is captured here. Can you see this is captured here? That information is captured here. If you can see, carefully observe this readings. For input voltage is 0.5, output is still not 5. For 3.2 it is 2.3. For 6.1 it is 5. For 8.7 it is almost 5. For 11 also it is almost 5. For voltages beyond 6.1 itself, the constant voltage is established. So even though we stated that okay, 7 volt is a requirement, but this regulator requires 6.13 volts to get a constant phi. You can see this is almost constant here. So that's what is this constant here. and the same thing is here constant. This is your xy characteristics or xy plot. So you can just click on this xy in your AD kit and you'll get this. And this are we have just put different cursors so that you can see the input and output, which results in this type of graph. So that's what I mentioned here. We're going to get this type of this is actually line regulation. Line regulation. This is line regulation. Then comes the load regulation. You know, so in this load regulation will be let me just tell you what happens in this load regulation. Okay, let me just show you what happens. So this is like, can you see this is your load regulation? Let me tell you what happens in load regulation. So let me go back here. Now this is line regulation because your input voltage has to vary from 0 to some less than regulation and more than regulated voltage. So now we intentionally filter the signal. So now we will apply a filtered waveform. We apply a filtered waveform after the capacitor to the regulator. So this is 7805. So now we will going to have a resistor. We're going to have a resistor which will decide my load current. So now this is what you have a voltage more than 7 but less than 20. So this is what is the range that what you have. So what you do now is you start reducing the resistance from a higher value. So what we are doing is we are keeping the resistance as 1110, and then we make it 510, then we make it 210 or 110, then we make it 60 ohm, 30 ohm, 20 ohm. So when you are reducing the resistance, your IL is keep increasing. So now the graph of load regulation. Load regulation. What do you mean by this load regulation? Is it is the variation of the output voltage as your load current increases. So if load current is 0, you're going to get V0 as 5 volt. Ideally this should be constant. Whatever is the load current, this should be constant. But typically what happens for larger load currents, this starts reducing. Can you see the output voltage reduces for larger load current? So when the resistance reduces, because what is IL? IL is nothing but V0 by RL. So this is RL. So when you keep increasing, when you keep reducing this resistance, so then this current increases. When this current increases, your output voltage will reduce. So let us do that here. So what we are doing here is, so we are just keep on changing the value from 110 to 510, all those things. So we have taken the plots corresponding to that. See now, this is 1110. Can you see I'm measuring what is the input to the regulator and output to the regulator? Can you see now the input is 12.3 something. Can you see the output is 4.98? So output is almost 4.98. Then you can see the resistance is reduced to, now the resistance is reduced to, okay, now let me just show you for this for 510. So now let us do it for, this is actually for 510. It is this value. Can you see this voltage, this, okay, average voltage has reduced from this is actually 11.96 here. What was earlier value? Can you see it is 12.3? So from 12.3 the input has reduced to a bit lower value. Sorry, okay, see here, from, just have a look at this. This is the input. You can just take this as the average. 1 minute. So this is, just have a look at this. So this is for a resistance of 1110. For 1110, let me just write it here. So V average is 12.36. Next comes for 510. For 510 it is, for 510 it is 11.96. For 110 it is 9 point, it is 9 point. This is the input average I'm talking about, the input average, and the output voltage is slightly, almost fairly constant here. For initially it is 9.39. Then can you see here, suppose if you further reduce the resistance to 50 ohm, when I reduce to 50 ohm, can you see the output average has reduced from 4.9 to 4.4. So now output has reduced to 4.4. Can you see this? Now this is a resistance of 30 ohm. Can you see the output average? Can you see it has become 3.5? Just again see what happens in the next case. Okay, I think I did it for only 30 ohm. For 30 ohm, the voltage has reduced to, sorry, this is your 30 ohm, sorry, 20 ohm. For 20 ohm, it is 2.7 volts. The output voltage average is keep reducing as you are increasing the current. As you're increasing the current, how you are increasing the current? By reducing the resistance. The output voltage reduced from 4.9 to, of course, 4.9, it's initially constant, then it becomes 4.7, 3.8, then it is 2.7. Can you see this is reducing? This is for a larger current. So that's what is load regulation. That's what is load regulation. And this type of analysis we do it for all circuits. Now this is half wave rectifier load regulation. Then comes the full wave rectifier experimentation conduction. So now this is the sine wave. You again note the maximum average voltage. This is C2 average, forget it. So C2 average is actually for the rectified signal. Then comes, you can see here, this is your rectified signal. See, this is rectified signal. Can you see only the negative half is there? This is exactly what we expected in our waveform. Can you see this is what is expected without filter? The moment you put the filter, this happens. Can you see this is the filtered one? Know the peak to peak of your C2. Can you see it is around 0.67? That's what we intended in our reading also. So we wanted to have a 0.5. Now you have 0.67. That's fine. And you can see this is a regulated voltage. Can you see this is at minus 5 volt? See here, this is you want to get a minus 5 volt regulation, you are exactly getting minus 5 volt. Can you see here? And you can see there is a very small ripple of 48 millivolt, whereas you have a huge ripple of almost around, of course this has got ripple of around 600 millivolt. Then comes, okay, now this is your load regulation. I will show you the line regulation also. Okay, maybe let me just minimize this and show you. This is I'm doing the load regulation for different values of resistance. You can see this is the line regulation. Can you see this voltage is negative? Can you see this is minus 5 volt? Can you see this is always below 0? Can you see these readings? These readings are corresponding to negative voltage. Can you see this is minus 5? So it requires minus 6.7 or less to get minus 5 volt. Can you see it's minus 5, minus 5, minus 5? So voltage has to be lesser than minus 6. That means minus 6, minus 6.4, minus 11, minus 16. For all those voltages, you are getting minus 5 volts. And then similarly, we are doing the load regulation. We are changing the resistance to a lower value. Can you see this? We are noting what is the average voltage of your output. So later for larger currents, the output voltage will reduce. Can you see the output voltage is now how much? C2 average, it's now still minus 5. If I further reduce the resistance, can you see it has become minus 4.7? See now, is it not become minus 4.3? Can you see the output voltage has reduced as expected over here? This is reducing as you are increasing the current. So this is common for any regulator. Only thing is that you have to start loading the regulator, whether it is positive regulator or negative regulator. Then so this is what and then comes the full wave, sorry, this is 12 volt regulation using bridge circuit. So since it requires we are using 909 and extreme, that is 18 volt RMS. 18 volt RMS is more than 25, that's why this is showing red here. So we may have to use a offset voltage to see the peak of your input signal. That's what is done here. Can you see there is an offset introduced? See here, I have introduced the offset of minus 10 volts so that it comes down. Now you're seeing the peak of this, You can see what is this. So the difference of maximum of input and maximum of output will be 1.4, which you can, I think you can able to make out that difference. Can you see one is 32.5, other one is 31.1. The difference is almost 1.4. So that's what is, you have two diodes conducting at a time. Then comes, so this is rectified one, fully rectified, and then comes the filtered one, then comes the filtered and regulated. Can you see the regulated is at 12 volts? Carefully observe. The output regulation is, this is C2 average is 11.954. So 11.954. Okay, now again the similar type of regulation I have done here. Again, you remove the capacitor there, then the input varies linearly and then becomes constant. The minimum voltage required to keep it constant is around 17 or 17.5 volts. Then comes the load regulation. Can you see I'm just keep changing the load from 1110 to 510. Then it is, you just keep an eye on what is C2 average. C2 average is reducing from 11.9 to 11.7, then it goes to 11.5, then it goes to 11.11, then it again goes down to, what is that value, then it again goes down to 11 volt C2 average. You can see from 12 it has become 11. Okay, this is the summary of all the readings. So this is again taken from the screenshots, the summary of the screenshot values. So V2 dash peak, again these are the values which I summarized it from the screenshot. So we are writing what is V2 dash peak for all the three circuit and what is V2 dash max from all the circuit. Okay, this is actually the maximum, negative maximum, and then you can see the ripple voltages and the output voltages. So here we wanted to have plus 5 volt regulator, minus 5 volt, and this is plus 12 volt. You can see you almost have that plus 5, minus 5, and this is 11.96. So this way you can able to comfortably do the report consisting of all regulation and filtering uh, regulation. Even in the regulation we have both line and load regulation being included. Hope okay, this will help you in making the report comfortably. Thank you.